You know, motion is literally everywhere. I mean, from a planet zipping around the sun to you just walking down the street. But how do we talk about all that movement with scientific precision? Well, that's what we're going to dive into.
Okay, let's start with something fun. A roller coaster. You know that feeling, right? The incredible speed, the sudden drops, those sharp banking turns. Your body just knows it's moving, and moving fast. It's this wild, super complex series of movements all packed into just a couple of minutes.
But what if you had to explain that ride to, say, an engineer? Just saying, it went really fast and then it dropped, well, that's just not going to cut it. To really describe what's happening accurately, we need a special set of tools.
So, to tackle this whole motion challenge, let's build ourselves a motion toolkit. And the very first thing we need, the foundation for everything else, is a starting point. Every good story has a beginning, right? Same thing here.
And that starting point, we call it a reference point. Think of it like an anchor. It's something that isn't moving, which lets us judge the motion of everything else that is. I mean, without it, how can you even really tell if something has moved at all?
And a reference point can be super simple. A tree, a building, maybe a stop sign. Anything that stays put is perfect. From there, we can say a car is moving away from the tree, or a person is walking towards the corner. See? The tree gives the whole observation meaning.
Okay, so we've got our anchor. Cool. The next two tools in our kit are all about how we measure the journey itself. And this is where it gets pretty interesting, because in science, the winding path you actually take and the shortcut you could have taken are two totally different things.
So first up, we have distance. This is the one we're all familiar with. It's really simple. It's just the total amount of ground you've covered. If you walk all the way around the block, the distance is the full length of that walk. Easy.
So imagine you're walking from point A to point B, and you follow this winding blue path. The distance is the entire length of that squiggly line. We're counting every single step you take.
But now, let's grab our next tool, displacement. This one is so important for scientists, pilots, or really anyone who needs to know not just how far you went, but where you ended up compared to where you started. Displacement is that straight line shortcut between your start and end points. And here's the key part. It always includes direction.
So let's look at our path again. That winding blue line, that was your distance. But this straight dotted red line, that's your displacement. It's the as the crow flies path, way shorter, and it points in one specific direction, from A straight to B.
Okay, here's a great way to lock this in. Distance is like your car's odometer. It just keeps adding up every single mile you drive, right? But displacement is like pulling up a map and just drawing one straight line from your starting point to where you finished.
All right, pop quiz time. Let's see if you've got this. A runner jogs 40 meters to the east, then turns right around and jogs 40 meters back to the west. What is their final displacement? Think about it.
The answer is 0. Kind of weird, right? I mean, their distance was 80 meters total, but because they ended up in the exact same spot where they started, their overall change in position, their displacement, is 0. To a physicist, it's like they never even left.
Okay, so now we know how to define where something is and how its position changes. So what's next? Well, the next logical tool we need in our kit has to be something that measures how fast all of this is happening.
And that, of course, is speed. Speed is what we call a rate. It connects that idea of distance we just talked about with time. It's really just how much distance do you cover in a certain amount of time.
And hey, if you ever need to calculate it, this little formula triangle is going to be your best friend. It's like a cheat code. You just cover up the thing you're trying to find with your finger, and boom, the triangle tells you exactly what math to do.
Let's try it out. A train travels 960 meters in 30 seconds. So what's its speed? Well, we take the distance, 960 meters, and we divide it by the time, 30 seconds. And that gives us a speed of 32 meters per second. See? Simple as that.
All right, we are building up quite a toolkit here. We can describe position, distance, speed. Now for our final tool, and honestly, it might be the most powerful one. It's a way to see the entire story of a journey all in one picture. Yep, we're talking about graphs.
Now, the secret to reading these graphs is understanding one little word, slope. Slope is just a fancy way of saying how steep a line is. And on a distance time graph, the slope is the speed. So, the steeper the line, the faster something's moving.
Take a look here.
On the left, you see that super steep line? That means an object is covering a lot of distance in a short amount of time. It's going fast. Now look at the line on the right. It's much flatter, more shallow. That means not much distance is being covered over time, so it's going slow. The steepness tells you everything.
So that leads to a question. What about a line with no steepness? A totally flat, horizontal line. Well, if the slope equals the speed, then a slope of 0 means a speed of 0. Time keeps ticking by, but the distance isn't changing one bit. That means the object is completely stopped.
And there you have it. That's your complete motion toolkit. Let's do a quick recap. You've got your reference point, which is your anchor. You've got distance, the total path you travel. You've got displacement, which is the straight line shortcut. Then there's speed, which tells you how fast you're going. And finally, graphs, which tell the whole story of the journey. So now you have the actual scientific language to describe pretty much any journey. So think about it, your own trip to school or to the store. How would you graph that? Where would the steep parts be when you're moving fast? And where would the flat lines be for all the stops? The world is just buzzing with motion, and now you have the tools to describe it all.